Hey students, so last week we talked about the rules for electrical charges. We discussed how things like protons and electrons have electrical charges that are positive and negative. And now normally, if we have them together, they can coexist in a certain level of balance, and this is okay. But if we separate them, and we make them uneven numbers, so now I've got two protons and one electron, we can start creating electrical problems. And we described these laws of things such as attraction and repulsion, where if I have two things that are opposite in charge, so positives and negatives, they're naturally going to stick together. But if I have two things that are both the same charge, so like I have two negatives here, they would naturally fly apart. So if we're going to go ahead and take those rules and talk about how we can apply those things in things like batteries, and so that we can actually make electricity do work for us using something called circuits. So in your house, probably in the room that you were in right now, there is something called a circuit. And the circuit, or a basic example for a circuit, is the one that I have drawn on the board for you. You probably have a circuit just like this within 10 feet of where you are sitting, because it works fairly simply. We have a source for positive charge over here. We have something that turns that electricity on and off on demand, so this is called a switch. We have a light bulb, which is going to light up, and then that electricity is going to travel all the way to the negative. And so we can use those charge differences that we talked about last week to make electricity do things using this circuit. So let's go ahead and give us a more complete version of this. I'm going to use a couple of Lego pieces here to represent the positive protons that we have in our circuit. I'm going to have a couple of red Lego pieces representing the negative. And just as a reminder, it doesn't matter if this is in your house or if it's using a battery, we still have the positive and negative terminals for things. So let's go ahead and use our knowledge of charge to figure out how this is going to work. Now our first rule is that negative things and positive things are naturally going to attract together, and negative things or positive and positive things are going to spread each other apart. So let's not go ahead and put these too close. They're not buddies. But I know that my negative thing wants to get to my positive thing. So it's going to start off along the track that I have given it. And it's going to flow through the light bulb. It's going to turn that light bulb on. And then it's going to get over here. And what we have here is we have a gap in our circuit. So this is considered an incomplete circuit. But if I turn my switch on, so if I go over to my wall and I flip the light switch so that I am allowing electricity to go through, that switch folds down, and all of a sudden my electron can go ahead and travel over here to the positive side and pair up with the proton that it was hoping to get to. And then the process continues. Now I want to point out one important thing about this. The electron is the one doing all of the moving. Protons don't move. So we're never moving, when we're talking about moving positive charge, we're not talking about moving protons themselves. We're only moving electrons in this example. Now, how quickly this happens, whether it's very, very slowly or whether they're moving around really rapidly, that is what we refer to as current. And current, and a lot of these words are going to become familiar to you. Current is something that is measured in amps. So if I have a 12 amp current, that describes to me how much electricity is moving through my circuit at any given moment. And the analogy that I'm going to go back to for a lot of these things is the idea of a hose for water. Current tells me how much water is going through the hose at a single time, or the current of a river tells you how quickly the water is moving in that river. So when we're talking about current, that's one thing we have to consider for our electrical circuits, is how quickly are these electrons able to move through here and make their way over to the positive end of the circuit. Now, if I take this switch and I turn my thing off, these electrons can't travel a full path. My current is 0. And if my current is 0, they can't complete because they can't make it all the way around. My light bulb doesn't work anymore. Now we're going to go over a couple of different things. One is going to be drawing some circuits of your own, but that's one thing that we have to keep track of. Now the other thing that we want to take a look at is something called the electromotive force, or what I am sometimes going to abbreviate as the EMF. The electromotive force, this is the force that moves the electrons through the circuit. They will naturally kind of wander ever so slightly on their own, but electrons need a push, and we need something to give them that push. In a normal circuit, for a lot of our handheld stuff, that thing that provides the push is the battery. So batteries provide the electromotive force. They push the electrons through the circuit on their own, which is why your electronics don't work if you don't put batteries in them. There's nothing to provide that push. So kind of once again, this is going to be our electromotive force. Electromotive force. I'll adjust my camera just a little bit here. And it's got this word motive in it. This is motives should sound a whole lot like motion to you. This is the thing that makes the electrons move, the electromotive force. And so what we get here is that one common mistake that I have with a lot of students is that a lot of students assume that our electrons originate in the battery. And no, that's not true. There's electrons in everything. There's electrons in you, there's electrons in your doorknob, there's electrons everywhere. The battery is the thing that provides the push that makes the electrons move around the circuit. So without that battery, we don't have an electromotive force. They don't move on their own. So far, what we've got is that we have something that pushes electricity through a circuit, we have a circuit, and we have a way of measuring how much electricity is going through it. So far we're doing okay. And I have my switch over here on the wall, and I can close this, or I can open the switch. I can close the switch, and that's allowing electricity to go through however it wants. But in a room like this, I have multiple light bulbs hooked up to the same switch. So what's that going to look like, and how do switches separate electricity? So let's take a look at a conventional circuit like the one in the room that I am in. Once again, all circuits have to have a positive side and a negative side representing the charges that are existing at those two terminals. And in this room, I have a wire that's going into a switch like the one that I was standing next to, and then that switch is controlling not one, but in this case I have two light bulbs here, and then they're going to go around to the negative side. So I've gone ahead and created this circuit in a similar way to the one I did in the first diagram, and let's say that I have a 12 volt power source in this case. So I got 12 volts. Now, if I have 12 volts, if these two these two light bulbs are the same, what I would normally expect, because of the way they are hooked up, is that they should share the electricity. 6 volts for this one, 6 volts for this one. That is if they are the same. Won't always be true if you kind of mismatch light bulbs and some get brighter than the other. But if I've got two equal batteries, they will equally share the amount of electricity flowing through it. Now, what this is called a voltage drop, or what they want you to identify as a potential difference. That's a fancy phrase. They use it a lot in England as far as the Cambridge curriculum is concerned. However, if you take any more physics here in the United States or in a couple of other countries as well, you will see this referred to as a voltage drop. And it is exactly what it sounds like in this description. This is the amount of volts that is being used to run this light bulb. So I am losing 6 volts as I cross this light bulb. And then I am losing a second 6 volts as I cross this light bulb, which means on the other side of this, I have used up all of the electricity in the circuit, and I have 0 volts now. And that is what you're going to be looking for. So as the voltage drop across the entire circuit is 12 volts. If I look at the voltage drop for just one of these light bulbs, the individual voltage drop is going to be 6 volts. So a voltage drop, or a potential difference, is the amount of electricity that we are losing as it goes through each one of these components. So hopefully at this point you're starting to get some of the patterns that we have in circuits. We have positive sides and we have negative sides. We have lines that represent the wires that our electrons are going to move around on. And when we put circuits in, or when we put circuits together, we want them to drive components like this light bulb right here that is going to use some of that voltage, and we're going to have a potential difference or a voltage drop that is going to cause this thing to do work. I'm going to write this correctly. Voltage drop, and this is going to cause the light bulb to turn on, shine light, and all that stuff. And we can control these things with things like switches, which if it's in the off position, does not allow electrons to flow through here, and if it's in the on position, does allow electrons to flow through here. And that's a pretty idyllic situation to be in, which means we haven't talked about one thing that, for better or for worse, is going to be in your circuits. And it is this. We haven't talked about resistance. Resistance is just like friction in real life. Resistance is a circuit's opposition to electrical flow. It's trying to slow the electrons down as it goes. And I just realized that this is really utterly poorly drawn. Let me try that one more time. That's much better. Resistance is measured in a unit called the ohm, and so this is the Greek letter omega, and omega is the symbol that we represent for our unit of resistance, which is called the ohm. Ohms tell us how much resistance there is to the flow of electricity within a circuit. If I'm talking about a circuit that really doesn't want to allow electricity through, that's going to be a high resistance circuit. There's going to be a lot of ohms in this. So for instance, if you talk about trying to send electricity through rubber, all right, there's going to be a really significant amount of resistance there. That is a high amount of resistance, or a high level of ohms. On the flip side, if you are at all familiar with most wires, you know that they're made of copper. That's a low resistance situation. So we're dealing with this concept of resistance. Resistance can be calculated using something called Ohm's law. And Ohm's law is fairly simple. The amount of resistance that we have in a circuit is equal to the amount of voltage trying to flow through that circuit divided by the amount of current that we have. So we have resistance over here. That's resistance. We have voltage over here. And we have our current down here. So this is the amount of electricity that we have. This is how quickly that electricity is moving. And if we use those two things together, we can solve for resistance. So if we want to think about it this way, if I have a ton of water, but it is moving very slowly, it's a high resistance situation. There is something that is actively slowing that down. So with that concept, we can kind of use Ohm's law to calculate how much resistance that we have in a circuit. Now, normally I would have you guys do some labs on Ohm's law, but seeing as we're kind of teaching from a distance here, I'm just going to throw that out there, knowing that if you take a physics class in college, you are going to be seeing Ohm's law later. Now, before I set you guys off on doing some of your own circuits, there's two things that we need to talk about. We need to talk about using the correct symbols for circuits, and we need to talk about two different ways of drawing circuits. So we have parallel circuits and we have series circuits. And so these are our last two things that I want to go over together as a group. So, starting with symbols. There are a couple of internationally accepted symbols for drawing circuits. There's only a handful that I really want you to know, but it's important that I kind of give them to you. Now, you've already seen a couple of these. This are the 0 with the X through it. This is a lamp or a light bulb. Something that is going to emit light. If I have a place where I can break the circuit or put it back together, typically represented like that, we have a switch. That is a place where I can open and close the circuit and determine whether I want electricity to flow through there or not. If I have a place where I'm making it intentionally difficult for electricity to go through, there's two different ways you will see that represented. They look like the squiggly line right here, this is very common in American electricity. If you see the square box over here, it's probably on a Cambridge diagram. That is something that's coming from the IGZI curriculum. These are resistors. This is a way of intentionally making it more difficult for electricity to flow through a circuit. Now there's also 3 ways that we can measure the 3 things that we talked about for Ohm's law. I can have an ammeter, which measures current. I can have a voltmeter, which measures voltage. And I can have an ohm meter, which measures resistance. So there's 3 different things that I can measure for Ohm's law, and they are represented by one of the letters inside of a circle. So those are the symbols that you have to know before you start dealing with circuits. Before I go on from those symbols, though, it's worth noting there are a lot more symbols because there's clearly a lot more things that you can put in a circuit than just lamps and switches and resistors and stuff like that. Now, our last little thing that I want to talk about, and this is extra, but a lot of you will find this helpful, is the idea of series circuits and parallel circuits. So kind of going back to our circuitry basics, I have a positive, I've got a negative, I have to have a path for that electricity to go around in order for it to work. Now, if I break this path right here, these 2 wires are not connected and they're not close enough together for electricity to jump the gap. Will I have a complete circuit? Do I have a way for electricity to go from one side of the circuit to the other side of the circuit? And hopefully at this point you are thinking to yourself, no, clearly there's a gap there. This causes us to have a couple of problems. So let's say that I have 3 light bulbs in a row. Okay, I have 3 light bulbs in a row in this circuit. I'm going to go ahead and put a switch in there because we should always be controlling stuff with switches. Alright, if I close this switch, I'm going to go ahead and take this switch and I'm going to lower it right here. I now have my pathways for my electrons to go around. So they can go ahead and make their way all the way through the circuit, as long as those 3 light bulbs work. What happens when one light bulb goes out? Will my other 2 light bulbs continue to work? No. No, they burn out as well. If you are familiar at all with old Christmas lights, searching for a burned out light bulb is something you might have done before. Because old Christmas lights are hooked up like this, and this is what's called a series circuit. Everything is in series. A series means one thing after another thing. So if you have a series in baseball, it's a series of games that are played one after the other, usually like one day, then the next day, then the next day, against the same team, and they're all to be considered together. So with a series circuit, I have a whole bunch of light bulbs that are going to have, where electricity is going to pass through them one after the other after the other. And if any of them blow out, the entire circuit is now broken and none of them will work. Which means if I have 1,000 light bulbs on a string of Christmas lights that are hooked up in series and one of them blows out, the entire string of light bulbs will not work, and I have to check 1,000 light bulbs before I find the one that I need to replace. Clearly, this is a pain. So, what they did is that they came up with a different way of wiring things. Let's go ahead and take the same elements. I've got the positive side, I've got the negative side, I've got my circuit, and instead of hooking them up in series, I can hook them up in what's called parallel. This is a parallel circuit. Now let's go ahead and kind of check with our electrons and see if we can still make this work. So if I've got my electrons, I'm going to start them on the negative side, really doesn't matter. Can electrons flow through here? Yes. Can electrons flow through the second one? Yes. Can electrons flow through the third one? Yes. If I blow this light bulb out right here and it's no longer working, can electrons still flow through the first one? Yes. Can electrons still flow through the last one? Yes. So these 2 light bulbs will continue to work And I realized my Lego did a little bit of damage to my circuit. Let me fix that. So there we go. As long as we still have a complete path for my electrons to go from one side of my circuit to the other, my light bulbs here are still going to work. So that's the advantage of a parallel circuit. Parallel circuits have components hooked up kind of in their own little branch of the stream, and that means that they're able to continue working. Now the problem with parallel circuits is that instead of having all of my electricity flowing in only one branch, now it has to split off. And so what I get, I'll put my light bulb back in there, is that I get less electricity floating back to or going through each bulb. And so there are costs to parallel circuits. In general, that they are a lot more power hungry. They're stable, but they're more power hungry. So there are pros and cons to everything that we do with electrical circuitry, whether you want it to be more stable or whether you want it to be more power hungry. So that's just an introduction to parallel and series circuits. You will see more about that if you take another physics class later, but I want to right now just kind of get you guys in the thought process for how circuitry works. So let's just do kind of like a quick recap of everything that we've looked at for electricity. Electrical charges are based on protons and electrons, two different things that we have. Normally, they are in balance, there's the same number of them, and they're kind of mixed together with positive and negative things kind of pairing up because they are naturally attracted to each other through the electrostatic force of attraction. Now, what happens if I want to create an electrical charge is that I just need to separate them out a little bit, and I can move them from one place to the other, whether that's rubbing your feet across the carpeting or rubbing a balloon on your head. If I can separate the charges, they very much want to go back together, and they will do whatever it takes to get back together, which is why we get things like lightning bolts and static electricity and things like that. But if we give them a distinct path for them to get back together, and I've got positives and negatives, we can create that path and we can generate a circuit. So if I put all my positive things over here, I can force my electrons to go through a certain organized path. And I'll draw a parallel circuit here. I can force them to go through an organized path in order to get back to what they want. So some of these electrons will go through this light bulb, some of these electrons will go through that light bulb, and as they go back together, they eventually want to end up back on the positive side of things, so that once again, we can have our pile of stuff. When we're trying to figure out how much electricity is moving through this, we can describe it in a couple of different ways. We talked about the idea of current, which describes how much electricity is moving through at any given moment. We talked about the idea of voltage, which describes how much the battery or the power source is pushing electrons through a circuit. Remember, voltage is provided by the battery or the source of electricity. And finally, we talked about resistance. And resistance was how much the circuit is naturally fighting back against the flow of electricity, because nothing is a perfect conductor. So resistance is just that measurement of how much effort the circuit is putting in to slow that electricity down. So we've got those three basic concepts. I also gave you a list of common symbols for circuits, and then we also talked really briefly about the concepts of series and parallel, so this being a parallel circuit, but if I was to take this out and instead put that same light bulb over here so that all of the electrons had to flow through in one path, that would be parallel. So that is kind of the really quick summary of the entire electricity unit. And for your assignment this week, you guys are going to be building a couple of circuits to show me that you understand how we can create circuits that fulfill certain requirements. So hopefully this video was helpful. I will be around for office hours if you need me. Good luck.